Hi everyone, welcome to Lesson 6, Key Features of Lines and Quadratics. Today we're going to talk about some of the key differences of lines and quadratics. Okay, so if you remember back to the rule of 3, there are 3 different ways that we can represent a linear relation. We have an equation, we have a table of values, and we have a graph. And the idea is we should be able to move from one to the other with a fair bit of fluency at this point. These 3 relations, this equation, this table, and this graph, all represent the same linear relation. Go ahead and pause the video for a second to make sure that you see the relationship between these. Okay, so hopefully you paused the video and had a look, and you can see, for example, that these three forms of the linear relation are all the same. And you know that for a few reasons. For instance, if we look at the equation first, we see that it has a y-intercept, a b-value, of -5. In the table, we see the same y-intercept show up. And in the graph, we see indeed that it does cross the y-axis at -5. So those 3 things check out, right? Boom, boom, boom. Good. Then if we look at the slope, we see the slope is 3/4. And if we look at the first differences here in the graph, we can see that from here to here, I have to add 3. And from here to here, I add 4. And from here to here, here to here, I add 3. And from here to here, I add 4. And I won't do the rest of them, but you can maybe see the pattern. Indeed, the rise is 3 and the run is 4. The rise is 3 and the run is 4, so that means that my slope equals 3/4. Okay, so that matches up as well. If I look at the graph, this one I admit is a little bit hard to tell because the graph is going up by 5s. The scale on the graph is 5s instead of 1s. So it's a little bit hard to tell for sure what the slope is in this graph. But just take my word for it, the slope here is in fact 3/4. If we had a better scale, we could for sure figure out that the slope is 3/4 just by counting up 3 and counting across 4 from one point to the next. Okay, so by the same rationale, or in the same way that there's a rule of 3 for a linear relation, there's also a rule of 3 for a quadratic relation. Now, let's just take a step back here, and whenever I talk about a quadratic relation, the graph of a quadratic relation is often called a parabola. Okay, so the shape of the graph is called a parabola, and we'll talk more about the shape in class. But I just want you to know that whenever I say quadratic relation, it's equivalent or interchangeable with a parabola, right? Parabola just refers to the graph, but sometimes it's a shorter word. Parabola is shorter than quadratic relation, albeit not by a lot. Okay, so if we start off with the same way, we're going to start with the equation. So here's a quadratic relation in its equation form. So what's different and what's the same in comparison to a linear relation? Just take a look at that there. Okay, so you might recognize a few things about this equation. For instance, you can tell that it's nonlinear because there's an exponent on the variable, on the independent variable, that's not a 1, right? This one is a 2. So just by virtue of that fact, we know that this is a nonlinear relation. And indeed, the fact that this is a 2 means that we call this one quadratic. Okay, so 2 in this description, a 2 on the variable, an exponent of 2 on the variable indicates that this is a quadratic relation. There are some other terms here. There's a linear term, Doesn't matter though. The fact that we have this quadratic term means that this is a quadratic relation. So in this case, the bigger number in the exponent is the one that matters to us. We also have this 1 off by itself here. And you might wonder what that guy is. It turns out that this, in the same way for a linear relation, this number by itself is the y-intercept. So this graph, if we were to graph it, and we will in a second, has a y-intercept of 0, 1. Okay, so we can do a table of values for that quadratic relation if I just write it down here. So there it is. That's our equation. I'm just going to use that for a second to generate a table of values. If you're not sure how to do this, just follow along. Basically, we have our x and we have our y, and we want to choose some values that for x that we'll substitute into the equation here and here, and then simplify the right side of the equation to get our y value. Okay, let's do a couple. Let's start off with 0. So when x is 0, that means that y equals 0 squared minus 2 times 0 plus 1. And if I simplify that, I get y equals 1. So y is 1. Okay, and that matches up with what I said earlier, that the y-intercept is a number on the end, 1 in this case. I could take another number, and for these sorts of things, we typically try and stick to whole numbers, at least at the start. So we say x equals 1, so therefore y equals 1 squared minus 2 times 1 plus 1, plus 1, and y equals 1 squared is 1 minus 2 plus 1, and that equals 0. So that equals 0 there. Okay, if you continued on this path, so for example, when x is 2, y would be 1. If x were 3, then y would be, I gotta do this here, y would be 4, and so on and so forth. Now there's one more really cool thing that you can do with a table of values. In this case, all I've done is just generate a table of values. So I haven't done anything very interesting except take the equation, put in some numbers for x, and then get out the appropriate values for y. But let's say that you were given a table of values, and I'll use this one just as my example. If you were given a table of values, you might be asked, how do you know that this table of values represents a quadratic relation? And there are a couple ways. Okay, so what we're going to do is we're going to first of all look at the first differences of this table of values, and we're going to do it exactly the same way we would for a linear relation. So you can see in the x's, if I go from 0 to 1, I'm going to add 1 each and every time, and I did that on purpose. If I look at the y's, however, different things are happening. So to go from 1 to 0, I have to subtract 1. From 0 to 1, I have to add 1. And to go from 1 to 4, I have to add 3. So this right away tells you, you look at this information, you say, okay, this is definitely not linear because the first differences are not equal, right? If you remember back to linear relations always have first differences that are equal to each other. In this case, they're not. It's definitely not linear. Okay, well, what if I kept on going? What if I looked at the second differences? Okay, so if I went from -1 to 1, I would be adding 2 in that case. And from +1 to +3, I add 2. Aha! This is interesting. The second differences are the same. And this is actually what you want to look out for. If you see the second differences are the same, this is a quadratic. Okay, so we'll talk a little bit more in class about what to actually do with this number, like how it helps you. But this is all I want you to come away with is when you have a table of values, second differences tell you if it's quadratic or not, just the way that the first differences would tell you if something is linear or not. Okay, so then lastly, we want to look at this graph. And again, this is the same graph. This is still y equals x squared minus 2x plus 1. And again, looking very carefully, we've got the plus 1, and we've got our intercept, so that seems to work. And what I want you to be able to do just at this point, because we're still just learning these, obviously, I want you to be able to look at the graph and say, is it a straight line? No, obviously not. It's doing this kind of thing. It's doing this U shape. It's a curve. And again, that shape tells us that this is nonlinear. It's a nonlinear curve, right? So there are two other things that I want you to be able to identify from the graph. First, we have the y-intercept. That's the first thing. We can already do that. And then I want you to be able to identify what's called the vertex. And that's this point here, this special point here down at the bottom, where the graph changes from, if you think about it, it's going down and then it goes up. So it basically changes its direction. It's going down, hits the vertex, and then starts going back up again. Okay, so if I spell that out for you, that's this, vertex. Just like that, okay? That's that guy right there. There's one other thing that is kind of nice, and if you look at this graph carefully, you'll see that it's mirrored in the sense that everything to the left of the vertex is mirrored to the right of the vertex. So if we were to draw kind of a mirror line, that would pass through the vertex. Well, that's not very good. So that would pass through the vertex, something like this. That's still not very good, but you get the idea. So everything on the left side of that mirror line is the same as everything on the right side of that mirror line. It's just mirrored. Okay, that's all. So we call that special line the axis of symmetry. And that's long enough. I'm going to type that out. So that's the axis of symmetry. Okay? Boom. There you go. Okay, so that's basically all the terminology I want you to know for today as far as the graph goes. Vertex here, that's the point where the graph changes direction. And the axis of symmetry, it's a vertical line which passes through the vertex. All right. Thanks very much for watching, and I'll see you in class.